Okay, so today we're going to learn about some nuclear reactions. We started the other day looking at nuclear reactions in the medical field. Today we'd like to look at nuclear reactions to produce energy for us. And the thing we're going to be learning about is a thing called nuclear fission. F-I-S-S-I-O-N, nuclear fission. This is the scientist who first theorized about nuclear fission. She thought that it would be possible to have a large nucleus like uranium and to hit it with a neutron and have it split into smaller isotopes. This was theoretical. Now you'll notice she's got two different names. The one is her family name, the second is her married name. I wanted to give you both. The one you'll probably hear more often is the married name that she used when she was a professional scientist. Okay? And again, this was 1934 in Germany, first person to theorize the possibility of nuclear fission. The first person to actually prove it happened is another scientist who worked in Germany, and her name was Liz Meitner. And you'll know she had to flee Germany during the war because of political situation. She was of Jewish background, and that was not a good thing in 1938 Germany. So she was working with part of a team through the 30s trying to create nuclear fission. When she left Germany, tried to escape for her life, she was given the data from the experiment. And during this time, she was able to analyze the data and show that nuclear fission had taken place in that reaction. So the first one to experimentally verify nuclear fission, 1938. Okay, let's take a look at what fission actually looks like. So this is the fission of uranium-235. So draw yourself a uranium-235, draw yourself a free neutron, and have that neutron traveling toward the uranium. It's important that it's not moving too fast or it will just hit and bump off. We want it to actually get absorbed into the nucleus. The nucleus will become incredibly unstable and then split. When it splits, you'll notice 3 neutrons popped off, and we were left behind with 2 other new isotopes. In this case, barium-141 and krypton-92. It does not have to split into these exact 2 isotopes, but this is one example of nuclear fission for uranium-235. Nuclear fission for uranium-235 is what takes place here. You may have seen this before. This is in Salem, our own backyard. If you ever go over the Delaware Memorial Bridge or you head down to extreme South Jersey, you've probably seen the cooling tower in the distance. This is the Salem nuclear plant, and they are splitting uranium to produce energy. Here's how the reaction looks. So we saw it through an animation. Here's how the reaction looks written as a nuclear reaction. We have 1 uranium combining with uranium-235. Again, 1 neutron combining with uranium-235. It creates for a brief moment uranium-236 in an extremely energetic form. It then splits into barium-141, krypton-92, and 3 neutrons. These 3 neutrons are important because these 3 neutrons can then hit other uraniums and keep this process going. You'll also notice energy is produced. How much energy? Well, I don't need you to calculate it, but I do want you to realize you take the initial mass, you take the final mass of all the products, you subtract them to get your delta mass, and then just like we've done with everything else, you plug it into Einstein's equation. This will tell you how much energy is liberated through this reaction. It turns out it is a tremendous amount. It turns out that 1 kilogram of uranium can give you 72 terajoules worth of energy. In comparison, 1 kilogram of coal gives 24 megajoules. which is nothing compared to 72 terajoules. So much more energy density with uranium. With coal, it's going to take a heck of a lot more coal to produce the same amount of energy. And the bad thing with the coal is when you're burning coal, you get all kinds of noxious gases. And even if the coal is clean, you still get carbon dioxide, which is going to cause problems for our planet. Okay, so nuclear energy turns out to have none of the bad side effects that we would get with burning fossil fuels. Unfortunately, it's got its own unfortunate side effects. And this is a chart showing the different levels of nuclear problems that can occur in a power plant. They start with things that are just called incidents, nothing too serious, happen occasionally. And then we transition into accidents, which could be severe, or they could just be a small accident with local consequences. And they're on a scale from 4 to 7. Our incidents go from 0 to 3. Well, it turns out there's only been a few major nuclear accidents. You may have heard of them. If not, you should know them, because they are historically kind of important. One took place in 1986 in the Soviet Union. It's now Ukraine, this area, and it's the Chernobyl accident. Another one took place while you were alive in 2011, and that took place at Fukushima in Japan. I don't want to get into too much detail, but I did attach little documentaries. I would suggest watching them. They are pretty fascinating in terms of the things that went wrong and the consequences that came of this. But these are the only level 7 disasters that you need to worry about. One in Chernobyl, one in Fukushima. There have been some level 5 accidents happen right in North America. One of them took place in 1952. It was at the Chalk River Laboratory in Canada, and they had some nuclear consequences from their accident. In fact, it was quite a dangerous and scary situation. And I put this naval cadet officer in here because he is one of the people who was tasked with helping to clean up this area in Canada. He was part of the U.S. Navy. He was part of our nuclear fleet of submarines. Okay, he was a nuclear scientist, so he was a perfect candidate to go in there and help with this cleanup. It turns out his name was James Earl Carter, and coincidentally, he would eventually become President of the United States. And coincidentally, during his presidency, was the only other North American nuclear disaster to reach level 5. This took place on March 28, 1978, and this one's called the 3 Mile Island disaster. This is just outside of Philadelphia, so it's kind of local to where we are. And he had experience with nuclear energy, so it's kind of really convenient that he happened to be president when this disaster took place right on American soil. He was uniquely qualified to deal with this. Okay, with the nuclear disasters we talk about, people think, man, nuclear power must be super dangerous. And although it does have consequences, so do all forms of energy. In fact, here's a chart showing you mortality rate in deaths per terawatt hour of energy produced. And you'll see that nuclear turns out to be the safest of them all. Coal turns out to be the most dangerous of them all. It's dangerous to the miners. There's possible deaths that take place during transport, and then there's deaths caused by the particulates that are emitted when you burn this thing. So when we sum them all up, it turns out that coal is most dangerous, followed by oil, natural gas, hydro, solar, wind, and finally, the safest of them all, believe it or not, in terms of deaths per kilowatt hour, is nuclear. Doesn't mean it's perfectly safe. Doesn't mean there aren't things we have to learn to deal with. One of them is nuclear waste. After we split the atom, those smaller isotopes are almost always radioactive. And we have to find a way to deal with those radioactive isotopes. Unfortunately now, the best option seems to be to put them in barrels and keep them cool enough so that they don't melt through the barrels, and making sure the barrels don't oxidize and have this radioactive waste become dangerous to us. So we literally have hundreds and hundreds and hundreds of barrels of nuclear waste that we have to deal with. Again, as long as we keep it away from people, it's pretty safe. So when we look at our isotopes that are produced, how long do we have to keep this nuclear waste away from people? Well, depending on the isotope that is produced, the answer varies. So for strontium-90, it's got a half-life of about 28 years. So maybe in 100 years, 4 half-lives have gone by. Maybe it's safe enough we don't have to worry about it anymore. Cesium-137, we probably have to wait a little bit longer. Plutonium, which is produced in some breeder reactors, has a half-life of over 24,000 years, and you're starting to see that's a problem. We got to find a way to keep that thing safe for 100,000 years. And it can get even worse with some of the other isotopes. Some isotopes that we produce have half-lives in the millions of years. How can we possibly deal with this nuclear waste and keep it safe for millions of years? Seems like a problem we're leaving to our great-great-great-great-great-grandkids. Okay, it's not just the nuclear waste that is dangerous, but also when we mine the uranium, some of the stuff left behind could also be radioactive. This is one that's within Delsey's school limits. Okay, so within Delsey's geographic area, there is a nuclear site from some mining that took place. And one of my students from a few years ago actually took a Geiger counter to the fence to measure if there was actually detectable radiation. And you could see that the Geiger counter is indicating that there is radiation there, much higher than the background radiation would be in most other places. If he had actually climbed the fence and gone to these piles of rocks, it probably would have been a much more dangerous situation. So there are problems with nuclear energy, but there are problems with all sources of energy. Okay, jumping back to our actual fission reaction. Neutron hits uranium. Uranium splits. 3 free neutrons. If these neutrons hit another uranium-235, it can keep this process going. These are what are known as chain reactions. The goal in a power plant is to have a controlled chain reaction so that you produce a steady stream of energy. If it was a nuclear weapon, you want an uncontrolled nuclear reaction, so all your energy is produced at one moment. Now you'll notice that if a neutron happens to hit uranium-238, that it will not break apart the same way the uranium-235 does. So in your power plant, you want to have as much uranium-235 as necessary to get your sustained reaction. The process of making sure you have enough uranium-235 is called enriching uranium. Uranium, when you find it naturally in the universe, is only a sliver of 235. Most of it is 238, and we don't really use that in most nuclear plants. So what you have to do is find a way to enrich it. That is, separate the 235 from the 238. If you can get it up to about 3 or 4%, you can use it in your nuclear reactor. And if you can get it up to about 90%, you can use it in a nuclear weapon. The way you actually enrich it is you combine the uranium with another element to produce a gas. And then you put the gas in a centrifuge, and by using the centrifuge you can separate it out based on mass. The heavier 238 will collect in one area, the lighter 235 will collect in another. It's not an easy process, but it is a process where you can start to separate out the two different isotopes of uranium. The stuff left behind, all that 238 that we can't use, is called depleted uranium. Okay? So again, this is our reaction. A controlled reaction is what happens in your power plant. The uncontrolled chain reaction happens in your weapon.